Hello and welcome back to our quiet corner of the cosmos. As the world outside grows still and the moon begins its slow climb through the sky, we will embark on a new kind of journey tonight. A journey not into the heart of a burning star, but into the gentle, quiet embrace of the cold. Tonight, we will drift toward the edge of the universe's great shiver, a place where heat is a distant memory and time moves with the patience of starlight. Take a moment to settle in. Fluff your pillow, find a comfortable position, and let your body soften. Close your eyes if you like, and simply listen to the sound of my voice. Imagine a small, warm place within you, perhaps just behind your ribs, a gentle glow of energy, a slow and steady hum. That is your core, your own private star. All of life, all of motion radiates from a place like this. Now, with your eyes closed, visualize a single drop of morning dew on a blade of grass. It sparkles like a tiny lens, a miniature universe of its own. Look closer. On the molecular level, this seemingly motionless drop is alive with silent activity. Its water molecules are in constant, frantic motion, bumping and spinning and dancing in a chaotic, invisible ballet. This restless dance is heat. The more they dance, the more energy they hold. The more energy they hold, the warmer they feel. This is the first, most fundamental truth of our journey. Heat is motion. Now, imagine that same dewdrop as the sun sets and the air cools. The frantic dance of the molecules begins to slow. The bumping becomes a gentle nudge, the spinning a slow, lazy turn. The vibrations calm, the wild energy softens, and the drop begins to solidify, to freeze. When the movement has all but ceased, when the particles are locked into a rigid, crystalline lattice, we call that cold. In science, we've learned that cold isn't really a thing at all. It is simply the absence of motion, a space where the music has faded and the dancers have stood still. The cold you feel when you step outside on a winter's night is your body, your little inner star, losing its heat to the still outer air. It isn't cold invading you, it is your warmth slowly leaving. It's a transfer of energy, a quiet sigh from the hot to the cold. Like a crowd leaving a theater, heat races out of you all at once. Your body simply registers the absence and names it cold. And we measure this absence in different ways. Most of us are familiar with the Celsius scale, where water freezes at 0 degrees and boils at 100 degrees. A scale that feels clean, symmetrical, and intuitive. Or perhaps you live in a place that uses the Fahrenheit scale, where water freezes at 32 degrees and boils at 212 degrees. A more idiosyncratic system, perhaps, but one with its own sense of rhythm and reason. But in the quiet places of the universe and in the deep rooms of science, we use a different scale, the Kelvin scale. The Kelvin scale is the universe's own language for temperature. It doesn't bother with the arbitrary freezing or boiling points of water. Instead, it starts at the beginning, or rather, at the end, at the ultimate stillness. It starts at absolute zero. This theoretical point, which is 0 Kelvin, or roughly minus 273.15 degrees Celsius, is the temperature at which all molecular motion ceases completely. A kind of perfect, motionless quiet. A place so cold that atoms would no longer dare to shiver. A temperature that we believe does not exist naturally anywhere in the universe in its pure form. So, as we begin this slow drift toward the frozen edge of reality, let this idea settle into your mind. Cold isn't an enemy. It isn't a thing that is. It's the name we give to a state of being, a state of profound rest and stillness. It is the end of the dance, a gentle pause button pressed on the microscopic jittering of all things. Drift with me now away from the warmth you know and toward this gentle quiet. We'll leave the familiar heat behind, the molten cores of planets and the searing surfaces of suns. We'll travel slowly, gently, to where the air itself has lost its fever and where the very fabric of space is holding its breath. Our journey begins with a single, slow step toward the universe at its most still. A place that challenges what we think we know about warmth and motion. The kind of place you might find in your dreams. Chapter 2: The Cosmic Thermometer. Let's continue our slow descent into the silent, chilly depths of the universe. In our last moment together, we spoke of the Kelvin scale, the one that starts at the ultimate stillness of absolute zero. To truly appreciate its meaning, we must first understand the vastness of the universe's full temperature range. It's a spectrum that spans more than 15 million degrees, from the unimaginably hot to the nearly non-existent cold. It's on this grand scale that our quiet journey begins to make sense. Imagine for a moment the hottest fire you can think of, perhaps the molten lava of a volcano, fresh from the Earth's heart, glowing at around 1200 Celsius. This is a dramatic kind of heat, full of destructive energy and brilliant light. But it is only a lukewarm puddle in the grand scheme of things. Now let's drift much hotter, past the chemical fires of Earth and toward the grand inferno of our sun. On the sun's surface, the temperature swells to an incredible 5500 Celsius. But go deeper still into the sun's core, and things reach a staggering 15 million degrees. At this point, heat is so intense that atoms can no longer hold on to their electrons. Hydrogen atoms are smashed together to form helium in a process we call nuclear fusion, and this is the heat that gives our sun its light and our world its warmth. Most of the universe, however, prefers a much cooler demeanor. As we begin to slide down the scale, we leave behind the scorching heat and pass through the comfortable middle ground where life, as we know it, thrives. We drift through the warmth of a summer's day at a pleasant 30 Celsius, past room temperature, and through the core temperature of your own body, a perfect balance at around 37 Celsius. Everything still feels familiar here within this narrow, cozy band. Keep descending with me now. We pass the freezing point of water at 0 Celsius and glide into the sub-zero air of winter mornings. At this stage, the molecules around you are moving so slowly that they begin to lock together, forming the delicate, symmetrical crystals of ice. As we go even lower to around -70 Celsius, a place that is colder than Antarctica on its most frigid days, things start to feel otherworldly. And if we drop further to a bone-chilling -196 Celsius, we find a place where nitrogen gas turns to a liquid, a substance so cold it can shatter a rose like glass. Below that, we enter the true realm of our journey, the cold of space. The deep emptiness between stars and galaxies is not just dark, it is filled with an almost perfect stillness. The temperature of this deep void hovers at a frigid 2.7 Kelvin. This is the temperature of the cosmic microwave background, the faint, gentle afterglow of the Big Bang itself. It is a whisper from the very beginning of time, a background hum of heat that still permeates the universe, setting a universal floor for temperature. You can't naturally find a cosmic location any colder than this. It's a base hum of warmth that the cosmos has never quite managed to shake. Now we approach our theoretical endpoint, absolute zero. At 0 Kelvin or negative 273.15 Celsius, all motion would cease. No jittering, no vibration. A kind of perfect, utter stillness. It is the finish line of the temperature race, a boundary that physics tells us we can approach but never fully reach. Why? Because the third law of thermodynamics states that to cool something to absolute zero, you would need to expend an infinite amount of energy. The closer you get, the more effort it takes. It's a mathematical and physical wall that stands as a testament to the universe's natural resistance to perfect stillness. But even if it's impossible to reach, the journey toward it has revealed some of the strangest and most beautiful secrets. At temperatures just a tiny fraction of a degree above absolute zero, atoms behave in totally bizarre ways, forming new states of matter and showing us a world governed by the strange rules of quantum mechanics. So as you rest, imagine the stunning range of this cosmic thermometer, from the raging heart of a star to the silent, frigid void between galaxies. And right in the middle, in that narrow band of gentle warmth, is you, tucked in, safe, and breathing. Our tiny familiar slice of existence is nestled between two grand extremes. The cold is not an empty absence, but a presence with its own unique rules. It's a place where energy fades and a new, more elegant form of physics begins to take shape. And the coldest places in the universe, it turns out, are a quiet, reassuring reminder that even the deepest voids follow a grand and beautiful order. Chapter 3. The Boomerang Nebula. Drift with me now, far from the familiar heat of our solar system, toward the southern skies. Picture a place 5,000 light-years from Earth, nestled somewhere in the direction of the Centaurus constellation. It's here, in the cold, unblinking vacuum of deep space, that we find a truly extraordinary cosmic oddity, the Boomerang Nebula. Nebulae are often places of dramatic endings and new beginnings. Some are the fiery birthplaces of stars, where clouds of gas and dust swirl together, pulled by the relentless hand of gravity. Others are the quiet cemeteries of the cosmos, the shimmering shrouds left behind by stars that have lived long, burned bright, and finally let go. The Boomerang Nebula is one of the latter. It's what astronomers call a planetary nebula, a term that, despite its name, has nothing at all to do with planets. It is the breathtaking final breath of a dying star. What makes this particular nebula so uniquely, astonishingly cold is its temperature. At just 1 Kelvin, or around minus 272.15 Celsius, it is colder than the lingering afterglow of the Big Bang, colder than the background temperature of space itself. And this is where the quiet paradox of the Boomerang Nebula begins to reveal itself. Space is already incredibly frigid, sitting at a baseline of 2.7 Kelvin. This faint hum of heat is a constant presence, the last echo of the universe's fiery infancy. So how can anything, especially a dying star, get colder than the very vacuum it floats in? The answer lies in the slow, powerful sigh of the central star. In its twilight years, this star began to shed its outer layers, but it did so in a rapid and spectacular fashion. It expelled gas at a staggering speed, over 500,000 kilometers per hour. When a gas expands rapidly into a vacuum, it cools down dramatically. It's the same principle behind your refrigerator, or the reason a spray can of air duster feels icy to the touch. As the gas spreads out, its energy is dispersed over a greater volume, and the temperature plummets. In the Boomerang Nebula, this effect is taken to a cosmic extreme. The expansion is so fast and so unimpeded that the gas cools far below the temperature of the surrounding cosmic microwave background. The nebula itself becomes a shield, an icy cocoon that blocks the faint warmth from the Big Bang's afterglow, allowing its core to descend into a realm of utter frost. When it was first discovered in the 1980s, astronomers noticed something odd. It was emitting far less radiation than they expected, a clear sign that it was cold. Later, sharper images from the Hubble Space Telescope revealed a beautiful hourglass shape, a cosmic butterfly made of pure frost and mist. Jets of frigid gas blasting outward from the central star formed symmetrical wings, a quiet testament to the slow, precise physics of a stellar farewell. This entire frigid display is temporary. As the gas continues to expand and thin out, the shield will weaken. The faint warmth of the cosmic background will eventually seep in, and the Boomerang Nebula will slowly, inevitably warm back up to the common cosmic chill of 2.7 Kelvin. For a brief cosmic moment, a fleeting oasis of stillness, it holds the record for the coldest naturally occurring place we have ever found. There's a deep poetry in this. Stars are supposed to burn, to radiate, to flood the cosmos with light and energy. Yet here, a dying star creates not a blaze of glory, but a magnificent exhalation of frost. It doesn't rage or roar, it sighs, and that sigh freezes into a magnificent shroud of silence. It is a beautiful paradox, a farewell made in frost rather than fire. Imagine standing within it if you could. There would be no sound, no sensation, no feeling of cold, for your body would disintegrate long before you could register the stillness. It would be the closest you could ever come to standing inside a whisper, a moment where motion and heat have almost completely vanished, leaving behind a magnificent, silent monument to a star's final breath. Chapter 4: The Voice of the Past. Let's continue our journey. Leaving the Boomerang Nebula to its temporary stillness, we now float in the deepest, emptiest regions of space, far from the warmth of any star. Here, the temperature settles at a baseline so profound and so ancient that it holds a secret to the universe's past. Long before galaxies spun themselves into graceful spirals, before stars began to twinkle their steady light, the universe was a hot, dense, chaotic soup. It was a place of blinding, seething energy with no cool air and certainly no silence. But as time unfurled its long ribbon, this fiery blaze began to expand and to cool. A blink of a moment in cosmic time, just 380,000 years after the Big Bang, the universe had expanded enough and cooled enough for a major transformation to occur. Atoms could finally form. The wild, free-roaming electrons settled into calm orbits around protons, creating the first neutral hydrogen atoms. This seemingly simple event had a profound consequence. The universe became transparent. For the first time, light could travel freely without constantly bouncing off a chaotic fog of particles. And that light, the very first light of the universe, is still traveling. We call it the Cosmic Microwave Background, or CMB for short. It is the oldest light in the cosmos, a faint afterglow from a time when everything was still young and unformed. It is everywhere, all around you, all the time, a quiet, gentle hum. The temperature of the CMB is an extraordinarily chilly 2.725 Kelvin, just a hair above absolute zero. In terms of energy, it's barely a whisper, a trace of what once was, but because it fills all of space, it is significant. It represents the minimum natural temperature of the universe. It's the base hum of warmth that the cosmos has not yet managed to shake, a constant reminder of our fiery origins. It's a peculiar thing to think about. This ancient light, older than any star or galaxy you can see, has been stretching and cooling for over 13 billion years. As the universe expanded, the wavelengths of this light stretched right along with it, moving from the fiery, visible spectrum all the way down to the long, low-energy microwaves we detect today. If the universe hadn't expanded, this relic light would still be blazing in ultraviolet or X-rays. Instead, it has cooled in rhythm with space itself, like a memory that has faded to a gentle echo. The story of its discovery is one of those delightful accidents that make science so magical. In the 1960s, two radio engineers, Arno Penzias and Robert Wilson, were working at Bell Labs. They kept encountering a mysterious static in their equipment, an unexplained noise that came from every direction, no matter where they pointed their antenna. They tried everything to get rid of the interference, but the noise persisted. What they had accidentally stumbled upon was the cosmic microwave background itself. It wasn't noise from Earth, it was the soft sound of the universe's infancy, reaching into their antenna from across the vast emptiness of time and space. For their serendipitous discovery, they were awarded the Nobel Prize. Since then, scientists have been mapping the CMB with ever-increasing precision. The maps show a sky filled with faint blotches of warmer and cooler regions, like ripples on a fine sheet of silk. These subtle temperature variations, no larger than 1 part in 100,000, were the seeds of everything. They were the subtle gravitational imperfections that eventually drew matter together, giving rise to galaxies, clusters, and the very structures that make up the universe we see today. It's like reading the baby pictures of all of existence. Because this radiation fills space so evenly, it acts as a kind of cosmic nightlight, a soft, steady glow that has never turned off. It is the light of the universe, frozen in time, stretched and softened, but never quite extinguished. We are literally bathed in the light of the early universe. The atoms in your body, the air you breathe, the warmth in your blanket, all of it exists against this ancient backdrop. It's not romanticized poetry, it's physics. The cosmic microwave background may not dazzle the eye like a shooting star or a glowing nebula, but its stillness is profound. It is the canvas upon which the rest of the cosmos was painted, a gentle echo from the dawn of time, still whispering across the void. It reminds us that sometimes it's the quietest things that carry the deepest stories. Chapter 5: The Chill of Interstellar Voids. As you rest now, imagine drifting further from home, past the faint, ancient glow of the cosmic microwave background, and into the vast, sprawling stillness between galaxies. This is intergalactic space, a profound and beautiful emptiness that stretches for millions of light years at a time. It is a place where warmth is a rumor and matter is almost non-existent. Here, in the most isolated regions of the universe, you would find a silence so complete it would be terrifying if you could truly experience it. The temperature settles to an almost perfect 2.7 Kelvin, a direct consequence of the universe's ancient light. But what is more remarkable than the cold itself is the sheer lack of anything to feel it. Intergalactic space is not truly empty, but it is as close as we can imagine. A cubic centimeter of air you're breathing right now holds trillions upon trillions of molecules. In the deepest intergalactic void, that same volume might contain just 1 or 2 atoms. It is a sparseness that defies our comprehension. You would have to scoop up a volume of space the size of a planet just to gather enough material to make a human-sized pinhead. And yet, in its quietest corners, this cosmic emptiness isn't entirely without activity. The cold, it turns out, is a key ingredient for one of the universe's most patient and profound transformations. Tucked away in the spiral arms of galaxies like our own Milky Way lie immense, shadowy regions called cold molecular clouds. These are the nurseries of stars. They are not warm, glowing places, but rather the opposite. Their temperatures can fall as low as 10 Kelvin. They're made mostly of hydrogen molecules, along with dust particles and traces of other complex molecules. The dust is crucial here. It acts like a cosmic blanket, shielding the gas from the radiation of nearby stars and keeping it cold. Without this deep chill, the atoms would move too fast, too chaotically, to ever come together and form the complex molecules needed to build a star system. In these frigid, dark clouds, atoms move gently, softly. They bump, they cling, and they slowly begin to build. Over millions of years, gravity works its magic, drawing these sparse particles into denser and denser pockets. As a pocket of gas and dust grows, it begins to collapse inward, slowly heating up as it does. Over time, that collapse creates enough pressure and heat to ignite a star. The cold, it turns out, is a necessary precursor for fire. For something as fiery and bright as a star to be born, you first need a place that is still and cold. These clouds are so cold that they are invisible to our eyes. They absorb and scatter visible light, appearing as dark smudges against a backdrop of stars. We can only detect them using radio telescopes, which pick up the faint emissions of the molecules within. It is a slow, quiet work, a glacial choreography of chemistry. Molecules like formaldehyde, methanol, and even the building blocks of amino acids are slowly, patiently forming on the backs of tiny dust particles. It's a beautiful contradiction. The coldest, most desolate places we can find are also the most hopeful. The chill of interstellar space isn't an ending, it is a beginning. It is the necessary background for stars to shine brighter, for galaxies to swirl more dramatically, and for planets to feel more alive. Without the cold, there would be no contrast, no edge to the warmth. There would be no silence to make the music of the universe stand out. So when you think of the emptiness of space, don't imagine a sterile void. Imagine a place of profound potential, quietly assembling the future out of hydrogen, gravity, and silence. In a strange and beautiful way, the coldest places in the universe are also its most pregnant with possibility.
Chapter 6: The Coldest Places on Earth. We've journeyed through the vast, cold expanse of space, from the frigid sigh of a dying star to the quiet birthplaces of suns. But some of the most astonishingly cold environments aren't found naturally in the cosmos. They are crafted right here on Earth, in carefully engineered laboratories where scientists are determined to touch the untouchable and get as close as possible to absolute zero. This isn't your average sub-zero freezer. When you get to temperatures a fraction of a degree above absolute zero, the rules of our everyday world begin to fall apart. Atoms slow down so much that they no longer behave like individual particles. Instead, they begin to blur into the strange world of quantum mechanics, where they act more like waves than solid objects. To achieve this surreal state, scientists have had to develop incredibly clever tools. One of the most elegant methods is called laser cooling. It sounds counterintuitive, doesn't it? Lasers are for heat, for cutting metal and burning through materials. But in the right context, a laser can be used to chill something down. Imagine an atom moving in one direction. If you shine a laser beam at it from the opposite direction, the atom absorbs a photon, which gives it a tiny push backwards. If you repeat this process with lasers from every direction, the atom is essentially stopped in its tracks. It's like gently nudging a bouncing ball until it's barely moving at all. By doing this, scientists can reduce the temperature of atomic gases to just millionths of a degree above absolute zero. To go even further, they use magnetic trapping. Once the atoms are slowed down by the lasers, powerful magnetic fields hold them in place, like invisible tweezers. From there, they use a process called evaporative cooling, which works on the same principle as sweat on your skin. The hottest atoms are allowed to escape the trap, which lowers the average energy and temperature of the remaining atoms. Using these methods in tandem, scientists have achieved temperatures that are measured in nanokelvin or even picokelvin, billionths and trillionths of a degree above absolute zero. And in this realm of unimaginable cold, something truly weird and beautiful happens. The atoms, no longer behaving as individuals, begin to merge. They lose their separate identities and become one unified entity, a single, collective wave of matter. This is a Bose-Einstein condensate, a state of matter so fragile and strange that it was predicted by Albert Einstein almost a century before it was first created in a lab in 1995. It's as if the atoms are marching perfectly in sync, every footstep, every breath unified, a single, serene river of matter. Scientists aren't just doing this to break records. The pursuit of ultra-cold temperatures is a window into the most fundamental truths of the universe. When you remove all the chaotic thermal noise of everyday motion, the subtle whispers of quantum mechanics become clear. In these labs, we can observe behaviors that are otherwise hidden: superconductivity, where electrons flow with zero resistance; superfluidity, where a liquid like helium flows with no friction, even climbing the walls of its container. This research isn't just for physics textbooks either. It's paving the way for revolutionary technologies like quantum computing, where maintaining this kind of perfect stillness is critical to making the fragile quantum bits work. The cold becomes a kind of magnifying glass for the laws of nature, a tool for revealing the fine print of physics. So, while the universe at large prefers a baseline of just under 3 Kelvin, the human mind, with its endless curiosity, is creating places thousands of times colder than anything found in nature. In the quiet chill of these labs, matter shows us what it's capable of when all distractions are stripped away. It is here, in the near-perfect stillness, that the universe whispers its secrets. Chapter 7. The Physics of Stillness. As we continue our slow drift, let's revisit the surreal behaviors of matter in the deep cold. It's as though the universe, in its frostiest corners, is peeling back its everyday mask to reveal its stranger, subtler self. The rules of physics as we know them begin to stutter, and a new, more mysterious performance takes center stage. To understand this, imagine a bustling street in a crowded city at noon. People are energetic, bumping into each other, each with their own purpose. That's how atoms and molecules behave at high temperatures, a chaotic, energetic jumble. But now imagine that same street late at night, in the deepest hours of a quiet, cold winter. The crowd has vanished. The few remaining people walk slowly, with deliberation. This is a bit like what happens when matter cools. The thermal motion, the noise of the system fades away. And in that quiet, a new kind of order emerges, governed by the precise, elegant rules of quantum mechanics. One of the most dramatic examples of this quantum weirdness is a phenomenon called superfluidity. It occurs in liquid helium when it's cooled to just below 2.17 Kelvin. At this temperature, the helium undergoes a phase transition, but not into a solid. Instead, it becomes a substance unlike any liquid you have ever seen. Superfluid helium flows without any friction or internal resistance. If you set it swirling in a container, it will keep spinning forever with no memory of its motion. Even more bizarrely, it can defy gravity and spontaneously creep up the walls of its container as if it's possessed by some otherworldly spirit of physics. This is possible because the atoms in the superfluid are so perfectly coordinated that they act as a single, unified quantum whole, flowing as one continuous, coherent entity. There are no individual sloshing parts, just a united wave of matter. A related phenomenon is superconductivity. This applies to electrons instead of atoms. Normally, when electricity flows through a wire, electrons bump into atoms and lose energy as heat, which is why your phone gets warm or a toaster glows. But in certain materials, cooled to just a few Kelvin, electrons suddenly stop resisting. They form pairs and begin to move through the material without scattering. It's like a rush hour crowd that suddenly begins to walk in perfect, choreographed synchrony. There is no traffic, no jostling, just a serene, lossless river of motion. This effect is powerful enough to levitate magnets, trap magnetic fields, and transmit energy with zero waste. It's not just a scientific curiosity, it's a technology that powers MRI machines, particle accelerators, and is a key to developing quantum computers. In these conditions, even time seems to behave differently, not in a science fiction sense, but in the way quantum systems evolve. As the noise of heat fades away, the fuzziness of quantum mechanics becomes more pronounced. Particles can tunnel through barriers they shouldn't be able to cross, and they can occupy multiple states simultaneously. This quantum coherence, the idea that particles can remain in a stable, linked state over time, becomes more visible. It's crucial for quantum computing, which relies on maintaining these delicate states. In a way, extreme cold is a powerful lens through which we can glimpse the fine print of physics. The rules haven't changed, but they are much easier to read when the atoms aren't shouting over each other with thermal energy. It's a kind of cosmic minimalism. At room temperature, matter is messy and complicated, but lower the temperature and complexity gives way to unity. Atoms align, particles merge, and motion becomes a gentle dance instead of a chaotic scramble. It is the universe at its most refined. So, if you ever think of cold as being empty or lifeless, remember this. The deepest magic often requires the quietest stage, and near absolute zero, the universe gives its most elegant performance, revealing its profound, secret life in a state of nearly perfect stillness. Chapter 8: The Unreachable Goal. For all the incredible feats that modern science has accomplished, splitting the atom, landing robots on distant planets, and decoding the human genome, there is one stubborn boundary we just can't cross, a line we inch toward with ever-increasing precision, yet never quite touch. That boundary is absolute zero, the ultimate stillness,
the point where all atomic motion stops. Why? Why does nature hold this particular prize just out of our reach? The answer lies in one of the fundamental rules of physics, the third law of thermodynamics. It may not get the dramatic spotlight like the laws of motion or gravity, but it quietly governs the deep, chilly end of the temperature pool. In simple terms, the third law states that as a system approaches absolute zero, the entropy, or disorder of that system, also approaches a minimum. But more importantly, it implies something very inconvenient. You can't reach absolute zero in a finite number of steps or in a finite amount of time. No matter how clever our cooling techniques become, there will always be some stubborn residual motion you can't quite eliminate. It's like trying to turn off the very last flickering light in a room where the switch keeps moving just out of reach. You can dim it, suppress it, and quiet it down until it's barely glowing, but actually switching it off? It's not going to happen. The problem is partly mathematical. As you cool something closer and closer to absolute zero, the energy you need to remove per degree gets smaller, but the effort required to remove it gets larger. The system becomes increasingly reluctant to give up that last bit of heat. It's a bit like trying to scoop up every last grain of sand off a beach. You get close, you scoop up almost all of them, but there's always one more hiding in the crevice of a rock. There's also a deep quantum mechanical reason that absolute zero is unreachable. According to Heisenberg's uncertainty principle, you can never know both the exact position and the exact momentum of a particle at the same time. If atoms were to come to a complete stop at absolute zero, you would know both exactly where they are and exactly how fast they're moving, which would be zero. This would break the fundamental rules of quantum mechanics, which doesn't allow for that kind of perfect certainty. So even the most chilled out atom must retain a little bit of jitter, a faint reminder that uncertainty never fully freezes. Despite all this, scientists have come impressively close. Laboratories have chilled atoms to within a few billionths of a degree above 0 Kelvin. At these incredible temperatures, atomic motion slows to a crawl, and entire systems of atoms begin to act as single, unified entities. It's the birthplace of exotic states of matter like Bose-Einstein condensates, where particles merge into one quantum wave. It's truly spectacular, but still not zero. Why does this matter? Because these extreme temperatures help us understand the very foundations of reality. Near absolute zero, matter behaves in ways that are otherwise hidden. The thermal noise of everyday temperatures masks the delicate subtleties of quantum behavior. But when the heat is gone, when motion slows and entropy drops, we get a clearer look at how particles interact, how forces behave, and what matter is capable of when it has nowhere left to hide. So the pursuit of absolute zero is a bit like chasing a mirage. You never arrive, but the journey itself is where the magic happens. And along the way, you start to understand not just how cold the universe can be, but how beautifully strange it becomes when everything slows down. It reminds us that some limits are built into the very fabric of reality, not as an obstacle to be conquered, but as a horizon to be approached. Chapter 9: The Sentinels of the Void. Deep space is cold. Not a wear a sweater kind of cold, but a deep, unblinking chill that hovers around minus 250 degrees Celsius. It's a place with no air to carry heat, no atmosphere to trap warmth, just an infinite, silent emptiness. And yet, floating through this profound stillness are some of humanity's most delicate and incredible creations, our spacecraft. You might think that keeping a machine cold in space is simple, but the vacuum of space doesn't conduct heat well. There's nothing for heat to travel through. So if you put an object in space, it doesn't immediately freeze. Instead, it slowly radiates its internal heat away. The challenge for engineers isn't just keeping a satellite warm, it's a precise balancing act. Too much heat, and the sensitive instruments will fry.
Too little, and lubricants freeze, batteries fail, and electronics stop working. It's like trying to keep a cup of tea warm in the middle of a desert with no air, no fire, and no electrical outlet for millions of miles. So, how do we do it? The first trick is insulation. Spacecraft are often wrapped in shiny, crinkly looking layers of a material called multi layer insulation, or MLI. If you've seen a satellite, you've seen this gold or silver foil. Each layer reflects thermal radiation, and the multiple layers trap heat like an ultra-light, high-tech sleeping bag, slowing the loss of warmth dramatically. But passive insulation only gets you so far. For missions that venture far from the sun's warmth, like those to the outer solar system, spacecraft need a more robust heat source. This is where radioisotope thermoelectric generators, or RTGs, come in. An RTG is essentially a nuclear battery. It uses the natural heat from the decay of a radioactive material, typically plutonium-238, to generate a steady trickle of both warmth and electricity. With no moving parts, no fuel tanks to worry about, and no need for sunlight, RTGs can last for decades. This is how the Voyager probes, launched back in 1977, are still powered as they drift ever deeper into interstellar space, far beyond where solar panels would be useful. Their tiny nuclear hearts keep beating, sending back whispers from the very edge of the sun's domain. Then there are spacecraft like the James Webb Telescope, a marvel of engineering that wants to be cold. Its instruments are designed to detect infrared light, which is essentially heat radiation. Any warmth from the telescope itself would create noise and obscure its view of faint cosmic signals. To stay chilled, Webb uses a gigantic 5-layer sun shield the size of a tennis court to block light and heat from the sun, Earth, and Moon. This allows it to cool passively to just about 40 Kelvin. One of its instruments is even actively cooled with a cryocooler to bring it down to about 7 Kelvin. It's a cosmic cold front, custom built to peer into the universe's most profound moments. The cold of space is a harsh teacher, forcing engineers to account for materials contracting, lubricants freezing, and components becoming brittle. Traditional grease doesn't work at minus 200 degrees Celsius. Instead, they use dry lubricants. Cables must be flexible and electronics must be shielded. It's like building a toaster that works inside a freezer the size of the solar system, and then asking it to never malfunction. And yet, in a strange twist, this relentless cold also helps. Without air, there's no corrosion, no weather, and very little degradation from the environment itself. The very vacuum that chills also preserves. The Voyager probes, drifting through interstellar space, may last for millions of years, their records protected in the freezing stillness. The cold is both an enemy and an ally, a threat that also allows for clarity, stability, and longevity. It is a profound paradox that reminds us how resilient and inventive the human mind can be. Chapter 10. The Dream of Cryosleep. There is something undeniably magical about the idea of cryosleep. It's the classic science fiction solution to a very real problem. How do you send people on a journey that takes decades, maybe even centuries, without them aging, going stir-crazy, or running out of food? The answer, in countless books and films, is elegantly simple. You just freeze them. Pop them into a futuristic pod, press a button, and they drift off into a perfectly preserved slumber while their ship cruises through the vast, cold void. But what if this isn't just a fantasy? In the world of biology, suspended animation is not unheard of. Some animals, like the Arctic wood frog, can survive being frozen solid during winter. Their hearts completely stop, their breathing ceases, and their bodies turn into solid ice. Yet, when spring arrives, they thaw out and hop away as if nothing happened. This is possible because their bodies produce a natural antifreeze, a type of glucose that protects their cells from the damaging ice crystals that form during freezing. Nature, it seems, has figured out a few tricks. Humans, on the other hand, are not built for freezing. Our cells are full of water, and when that water freezes, it forms sharp, destructive ice crystals. These crystals puncture cell membranes like tiny daggers, causing catastrophic damage. To get around this, scientists have developed a process called cryopreservation. It involves cooling biological tissue to very low temperatures, usually around minus 196 degrees Celsius, the boiling point of liquid nitrogen, while preventing ice from forming. This is done with special chemicals called cryoprotectants, which act like antifreeze, replacing the water inside the cells and protecting them from freezing damage. Cryopreservation is already a cornerstone of modern medicine. We routinely freeze and store sperm, eggs, and embryos, and even small pieces of tissue for years. But there's a catch. This process works best with very small, simple structures. Whole, complex organs like a heart or a liver are much more difficult to freeze and thaw without injury. And a whole human body is a problem of immense proportions. The main hurdles are ensuring even cooling throughout the entire body, and then, even more challenging, a safe and uniform rewarming. This hasn't stopped some people from signing up for this technology anyway. Companies offer full body or just brain preservation after legal death, with the hope that future technology will be able to repair the freezing damage and revive the person when science has caught up. It remains a speculative leap of faith, a kind of scientific time capsule filled with frozen hope, because no human has ever been successfully revived from this state. So, what would it take to make cryosleep for space travel a reality? You would first need a way to cool a person to near zero metabolic function without forming ice crystals or damaging tissues. Then you'd have to keep them stable for years, possibly generations, without power failures or system malfunctions. Finally, you'd need to safely rewarm them and fully restore their biological and cognitive functions. Even if all these technical problems were solved, a host of profound ethical questions would remain. If a person wakes up 1,000 years in the future, are they still the same person? What happens to memory, to identity, to the sense of time? And yet, the allure remains. Long-distance space travel is impractical when measured in human lifespans. Cryosleep could, in theory, allow us to explore distant worlds, colonize other planets, or ride out long voyages without consuming endless supplies or going completely mad from boredom. In this way, cryosleep isn't just about freezing bodies, it's about preserving dreams, about tucking ourselves away for a future we hope will be kinder and more advanced. For now, it belongs to the realm of stories, of glowing pods, and a distant, hopeful waking. Chapter 11: The Icy Hearts of the Solar System. Our own solar system, with all its familiar fiery planets and swirling gas giants, has a quiet secret. It's also home to some of the coldest, most isolated worlds we've ever discovered. These frozen realms don't glow like the sun or sparkle like Saturn's rings. Instead, they lurk in the dark, icy and silent. And yet, beneath their frozen crusts, there might be something astonishing, a glimmer of life. Let's begin our descent with Europa, one of Jupiter's largest moons. At first glance, Europa looks like a ball dipped in a frozen crackle glaze. Its surface is a smooth white shell of ice, etched with long reddish-brown lines that snake across its surface like veins on a marble sculpture. The temperature there is not what you would call balmy. Daytime highs hover around minus 160 degrees Celsius. The surface is a solid, ancient, and brittle shell of ice. But beneath that icy crust, something fascinating is hiding. Evidence suggests that Europa harbors a vast global ocean. This isn't a puddle, it's a deep, possibly saltwater ocean containing more liquid water than all of Earth's oceans combined.
And this ocean is kept in motion not by sunlight, but by the powerful gravitational pull of Jupiter. As Europa orbits its immense parent planet, it gets stretched and squeezed, generating internal heat. That warmth is believed to be enough to keep the ocean from freezing solid, creating a potential habitat sealed beneath kilometers of ice. Then there is Enceladus, a small moon of Saturn that punches far above its weight and scientific intrigue. It is tiny, only about 500 kilometers across, roughly the width of Arizona, but it is one of the most geologically active bodies in the solar system. Its surface is a gleaming white with fractures near the South Pole that vent enormous geysers of water vapor, ice particles, and organic molecules out into space. These plumes shoot hundreds of kilometers above the surface, forming a misty halo that feeds Saturn's outer rings. The average surface temperature is around -200 degrees Celsius. But just like Europa, it's believed to have a subsurface ocean kept liquid by tidal flexing from Saturn's gravity. What's even more exciting is that the Cassini spacecraft actually flew through these plumes and detected signs of organic chemistry, the carbon-based molecules that form the foundation of life as we know it. Even farther out lies Pluto, the king of the Kuiper Belt. At a distance of nearly 6 billion kilometers from the sun, Pluto receives less sunlight than a candle in a cave. Surface temperatures plunge to around -230 degrees Celsius. And yet, when the New Horizons spacecraft flew past in 2015, the little world surprised us. It wasn't just a frozen rock. It had mountains made of water ice, plains of nitrogen snow, glaciers, and even what looked like a giant heart-shaped region. The images showed a complex surface shaped by ongoing geologic activity. Some scientists believe there could still be pockets of liquid beneath Pluto's crust, slowly freezing, but perhaps not entirely solid just yet. The idea that these cold, distant worlds could harbor life might seem strange. We tend to imagine life in warm, sun-drenched environments. But life on Earth has proven to be surprisingly adaptable. Microbes thrive in the deep ocean where sunlight never reaches. Other extremophiles live in the ice of Antarctica, in acidic lakes, and inside nuclear reactors. Life, it seems, is more flexible than we once believed. On Europa and Enceladus, the combination of liquid water, heat, and organic molecules creates a tantalizing possibility. If hydrothermal vents exist on their ocean floors, like the ones on Earth's seafloor, they could provide the energy and nutrients to support entire ecosystems. On Earth, these vents host vibrant communities of tube worms, crabs, and bacteria, all sustained by chemosynthesis, life powered not by sunlight, but by chemical reactions. The lesson here is profound. Cold doesn't mean dead. The absence of surface warmth doesn't rule out the presence of life. In fact, some of the best candidates for extraterrestrial life in our solar system are not the scorched rocks near the sun, but these distant, icy spheres, sheltered, secretive, and perhaps quietly alive beneath their frosty skins. They are a humbling reminder that our view of life is shaped by our own planet's quirks, and that the real heartbeat of the cosmos could be echoing from places we once dismissed as too cold, too quiet, and too far away. Chapter 12: The Cold, Dark Weaving of the Cosmos. If you've been drifting along on this chilly tour of the universe, you may have come across the term cold, dark matter. It sounds appropriately mysterious and dramatic, like something whispered by astronomers over mugs of black coffee at 2 a.m. And it's a concept that shows up all over cosmology, scientific papers, and even science fiction. But while the name suggests a shadowy substance locked in a state of deep freeze, the reality is both more abstract and more fascinating.
Let's start with the dark part. Dark matter isn't dark in the way a shadow is dark. It's dark because it doesn't emit, absorb, or reflect light. It's completely invisible, a ghost to our telescopes. But we know it's there because we can see what it does, even if we can't see what it is. Galaxies rotate in a way that suggests there is far more mass present than we can account for with stars, gas, and planets. Stars at the outer edges of galaxies move faster than they should if all the mass were concentrated near the center. Something is adding extra gravity, something invisible. That something is what we call dark matter. It's the scaffolding that holds galaxies together and shapes the large-scale structure of the universe. So, where does the cold come in? In cosmology, cold doesn't refer to temperature in the traditional sense. It doesn't mean these mysterious particles are frosty or that they'd give you a chill if you could somehow touch them. Instead, cold refers to their speed. Cold dark matter particles are theorized to be non-relativistic, meaning they moved relatively slowly compared to the speed of light in the early universe. This slow motion allowed them to clump together more easily, forming dense knots of gravitational glue that helped galaxies and galaxy clusters form. These clumps acted like seeds, drawing in normal matter, gas, dust, and stars, and giving rise to the cosmic structures we see today. This is in contrast to hot dark matter, which would have been moving close to the speed of light. Particles moving that fast would have smoothed over any small fluctuations in density, making it difficult for galaxies to form. A universe dominated by hot dark matter would look very different, far more empty and homogeneous. Then there's a kind of theoretical middle ground, warm dark matter. Not too fast and not too slow, which could still allow structure to form, but perhaps not in the same way as cold dark matter. The current leading theory, the one that best fits our observations of the universe's structure, is that dark matter is cold, but we haven't found the actual particles yet. They remain elusive. Many candidates have been proposed over the years, from the heavy WIMP, or weakly interacting massive particle, to the ultralight axion. If they exist, trillions of them would be passing through you every second without you ever noticing. What we do know is that dark matter makes up about 27% of the universe's total mass and energy content. That's over 5 times more than all the ordinary matter we are made of. Everything we've ever touched, tasted, built, or seen, all the stars and planets and people, make up less than 5% of the universe. The rest is dark matter and an even stranger thing called dark energy, which means that almost everything in the universe is made of something we've never seen. And yet, this invisible stuff plays a vital role. Without cold dark matter, galaxies wouldn't hold together. The universe would be a much smoother, emptier place. Computer simulations that model cosmic evolution with cold dark matter produce structures that closely resemble the universe we actually observe. Dense filaments of galaxies stretching across space, enormous voids in between, and intricate web-like patterns of matter on vast scales. It's as if the cosmos is knitting itself together with an invisible thread, and cold dark matter is the needle. It's humbling, really. The universe we see, the beautiful, brilliant part with all its light and motion, is just a faint glow riding on top of something vast and unknown. Cold dark matter isn't just about temperature or mass, it's about the parts of reality we've yet to grasp. The silent majority of the cosmos holding everything together from behind the scenes. So the next time you look up at the stars, consider the invisible hand shaping their patterns. It may be cold, it may be dark, but without it, the universe would have no structure at all. Chapter 13. The Gentle End of the Universe. If the universe had a bedtime story, this would be its final chapter. Not a loud, fiery bang, but a slow, steady sigh. Not a dramatic, meteor-filled apocalypse, but a gentle fading into stillness. This is the theoretical finale of everything. a concept known as the heat death of the universe. And despite its name, it has very little to do with heat as we know it. It is actually the ultimate cold, a cosmic quietude where everything that could happen already has, and all that remains is a slow, cold unfurling into silence. To understand how we get there, we must begin with the second law of thermodynamics. This rule, which governs how energy moves and transforms, tells us that entropy, or disorder, always increases in a closed system. Left to its own devices, the universe tends to spread out its energy evenly, like sugar dissolving into tea. Over time, differences in energy will even out. Hot things will cool, organized things will decay. Complexity will give way to simplicity. That is entropy's way. Right now, the universe is full of interesting things. Stars are burning, galaxies are colliding, and black holes are munching on the occasional unlucky gas cloud. There's light, warmth, motion, and imbalance, which is just the way entropy likes to play. But this won't last forever. Fast forward a few trillion years. The stars will begin to go out. The big, bright stars burn out quickly, but even the smaller ones, like red dwarfs, will eventually run out of fuel. When the last star dies, it will leave behind a cold, dark remnant, a white dwarf, a neutron star, or a black hole. Over immense spans of time, even the glowing embers of white dwarfs will cool and fade into black dwarfs, radiating no light or heat. The galaxies themselves will grow dim. With no new stars forming and old stars winking out, the night sky will slowly lose its sparkle. The cosmos will become a quieter, darker place. Black holes, once thought to be eternal, will also fade away. Thanks to a prediction by Stephen Hawking, we now believe black holes slowly lose mass through a process called Hawking radiation. They emit tiny amounts of energy over time, shrinking ever so slightly with each passing eon. This evaporation is extraordinarily slow, but given enough time, vastly more time than the universe has had so far, even the largest black holes will fizzle out and vanish into the quantum mist. What will be left? Not much. Some particles, some lonely photons, a smattering of neutrons and protons, drifting through a space that is unimaginably vast and mostly empty. The temperature will have approached absolute zero, hovering infinitesimally above it. At that point, no new stars will ignite, no structures will form, and no work will be done. Every gradient, every imbalance that once drove activity will be gone. This is heat death, not a sudden collapse or a catastrophic event, but a state of maximum entropy. Everything is evenly distributed and no usable energy is left to fuel change. The universe, still expanding, will contain nothing but a sparse, cold soup of particles and faded radiation. It's a strange name, really. Heat death sounds like it should be fiery and final, but it is more like the gentle dimming into candle that was never relit. In this final stillness, in the cosmic hush that follows eons of light and motion, the story ends. It is not a fiery apocalypse, but a frozen whisper, a sigh of entropy echoing softly across an empty stage. It is a strange and peaceful image, a cosmos that has lived a full, fiery life and now rests in perfect equilibrium. It's a reminder that not all endings are violent. Some come slowly, like winter settling in, not with a roar, but with a hush. The cosmos doesn't rage. It drifts, frozen and eternal. Chapter 14. The Paradox of Cold. We have traveled a long way together, from the subtle stillness of a freezing dewdrop to the vast, quiet expanse between galaxies. We have seen how the universe measures temperature and how its laws bend and shift when the heat fades away. Now, as our journey nears its gentle conclusion, let us take a moment to reflect on a beautiful paradox that has appeared time and again throughout our exploration. It is the idea that cold, which we so often associate with absence, death, and decay, is in fact a necessary and creative force, the ultimate enabler of new beginnings. We are, as creatures, biased toward warmth. Our senses are designed to appreciate light and heat. Our bodies require a very specific, narrow band of temperature to function. We see the warmth of the sun as a gift, the glow of a fire as a comfort, and the heat of a volcano as a dramatic, powerful spectacle. Our stories of the cosmos are often stories of fire, of stars burning, of planets being forged in molten rock, of galaxies blazing with light. And yet, this is only half the truth. Go back for a moment to the deepest parts of our galaxy. Picture those vast, dark stretches of interstellar space, the so-called cold molecular clouds. To our eyes, they would appear as nothing, just a void, a smudge of black against the distant stars. But we now know that within those frigid, dusty wombs, new life is being born. The temperature within these clouds can drop to just 10 Kelvin. It is a stillness so profound that gas atoms and dust particles have no choice but to slow down. Their wild, chaotic energy is gone, and they begin to cooperate. They gently collide, clinging to one another, and over millions of years, they assemble the ingredients for a new star. A star that will eventually become a bright, fiery beacon. But that fire would never have existed without the cold that came before. The cold is a prerequisite for creation, a necessary silence before the universe can begin to compose its next song. Think also of the Boomerang Nebula, the majestic, frigid butterfly made of a dying star's breath. It defies our expectations. We anticipate a grand fiery finale. Instead, this star whispers its final secrets in a language of pure frost. And in doing so, it creates the coldest place in the known universe, a place that pushes the boundaries of our understanding. It shows us that endings in the cosmos are not always loud and dramatic. Sometimes they are quiet, elegant, and strangely beautiful. The cold, in this case, is not an end in itself, but a brief, magnificent transition, a final act of grace before the star's material is reabsorbed into the cosmic quiet. And what about our own scientific pursuits? We use extreme cold not to destroy, but to reveal. In the deepest, coldest laboratories on Earth, we don't just cool things down. We peer into the universe's most profound behaviors. We use stillness as a tool, a magnifying glass to see the delicate choreography of quantum mechanics. When we chill atoms to a fraction of a degree above absolute zero, we don't get nothingness, we get something new. We get Bose-Einstein condensates, where matter unifies into a single entity, a serene river of particles flowing as one. We get superconductors, where electricity moves with zero resistance, revealing a perfection of flow we never thought possible. Cold here isn't a force of stagnation, but a key that unlocks a new realm of physics, a place where the universe's underlying elegant patterns are no longer obscured by the loud noise of heat. Even in the search for life, we are being taught a lesson. For decades, we looked for signs of life on planets that were warm, wet, and Earth-like. But now, our most promising candidates lie beneath the icy shells of moons like Europa and Enceladus. We are learning that life may not need the warmth of a sun to begin. It might just need liquid water and a source of energy, even if that energy comes from the gentle tidal kneading of a massive planet. These icy moons,
once dismissed as frozen tombstones in the outer solar system, now hold our most profound hope. The cold of their surfaces is a perfect shield, protecting the secrets of their subsurface oceans from the harsh radiation of space, allowing life to possibly flourish in a quiet, undisturbed darkness. The paradox of cold, then, is that it is a force of creation and preservation. It slows time down for living tissue, protects fragile molecules in space, and reveals the hidden architecture of matter. It is the patient artist sketching out the blueprints for new stars in molecular clouds and allowing new states of matter to emerge in laboratories. It is the backdrop against which all warmth and motion must be judged. So as you rest, let this thought settle gently in your mind. The universe is not just fire and fury, light and speed. It is also stillness and patience, darkness and cold. And in those cold and quiet places, some of its most magnificent and unexpected stories are waiting to be told. The universe seems to know something we are only just beginning to grasp. That to create a new kind of beauty, a new kind of order, sometimes all you have to do is turn down the heat. Chapter 15. The Universe as it sleeps. As our long, quiet journey through the frozen cosmos comes to its gentle close, let's imagine our final destination. A universe fully asleep. This is not a place of chaos or catastrophe. It's not a place filled with crashing planets or screaming supernovas. No, this universe is calm, utterly, infinitely calm. It is the quiet after all songs have ended, a place where temperature, that great driver of motion and life, has settled as close to zero as physics allows. What would it feel like to be there? Not in the human sense, of course, for there are no nerves to tingle, no skin to goosebump, but in the grand abstract shape of things, it would feel still, motionless and silent, but not empty. The galaxies have stopped spinning, the last stars have burned out, the black holes have evaporated into a dusting of radiation so faint it barely registers. What remains are particles drifting in a vast, ever-expanding space with nowhere to go and no energy left to change anything. This is not a frozen hell. It is more like a cosmic whisper, a gentle end, like exhaling after holding your breath for billions of years. In a fully cold universe, entropy has won. Energy has spread itself as evenly as possible, and nothing is left to power change. The background temperature of the universe has cooled to an almost perfect absolute zero. Only the faintest trace of heat remains, the echo of what once was. Could life adapt to this? Could something survive here in this pure stillness? Life, at least as we understand it, is powered by contrast, warm versus cold, high energy versus low. Every living thing on Earth thrives in imbalance. Plants feed on photons from a hot star. Animals shuffle energy around like a cosmic relay race. Life is a tightrope walk of energy exchange. In a universe where temperature gradients no longer exist, where everything is the same everywhere, there is no flow. And with no flow, there is no work. Without work, there is no metabolism, no thought, no life. Even if a life form could somehow perfectly insulate itself and store energy for trillions of years, it would eventually spend that energy, and then it would join the great stillness. And yet, the idea of a universe without warmth is not entirely bleak. There is a strange elegance in the image, a cosmos that has lived a full, fiery life and now rests in perfect equilibrium. It is not in mourning, it is resting. All the battles have been fought. The stars have told their stories. The galaxies have pirouetted across the void, and now, like dancers after a performance, the universe lets the curtain fall. There's a kind of peace in that. No rush, no noise, just vast, cold space humming ever so gently with the memory of light. We often associate cold with discomfort, with frostbitten fingers and silent streets. But taken to its cosmic extreme, cold becomes something else. It becomes a stage where the deepest truths of the universe can be seen clearly, where heat and light no longer cloud our view, a place where matter becomes minimal, and what remains is pure geometry, pure structure, and pure time. It is here that the poetry of physics becomes most profound. In this frozen quiet, we can ask questions without expecting answers. What is the shape of a universe that no longer changes? What does time mean when nothing moves? When there is no heat, no clocks ticking, no atoms vibrating, what becomes of duration? These are not just scientific questions, they are philosophical. They nudge at the limits of understanding. When you think about the cold end of the universe, you're not just thinking about temperature. You're contemplating the nature of existence itself. And still, even in that silence, there is beauty. The symmetry of space stretched across unimaginable distances, the quiet dignity of particles content to drift, the persistence of gravity holding on until the very end. There is something deeply moving about a universe that doesn't rage against the dying of the light, but simply allows itself to cool and rest. It's a reminder that not all endings are violent. Some come slowly, like winter settling in, not with a roar, but with a hush. And yet, even as we imagine this final chapter, we're still here, warm and awake, breathing in a sliver of time when stars still shine and molecules still hum with life. Our tiny planet is perched in a very special moment, a moment when warmth still flows and energy still dances. That in itself is worth appreciating. In the grand arc of cosmic time, our warm, glowing now is brief, precious, and extraordinary. Perhaps that's the most meaningful takeaway from imagining a cold universe. It reminds us how rare warmth really is, how fragile, how beautiful, and how worth cherishing. Because one day, if the theories hold true, warmth will fade. And when it does, the universe will close its eyes, not in sorrow, but in peace.